Now let's discuss the integral control. In the integral control, the control signal is proportional to the integral of the system error. So Ki is proportional gain. At any given time, for example, T1, the control signal is the integral of the area under the system error. The purpose to introduce the integral control is to reduce the steady state error and also improve the steady state output response performance due to disturbances. As we know, to reduce the steady state error, if we use proportional control, we have to use a very large Kp. So one way to improve the steady state accuracy of control without using extremely high proportional gain is to introduce integral control. The Laplace transform of the integral control is Ki over S. As we know, 1 over S is the integrator. This means the integral control contains one integrator. So now let's assume the Planck transfer function. So the DC gain of the open loop transfer function is a finite non-zero constant. It means that the GS contains no zero, no pole at the origin. No zero, no pole at the origin. Then what is the type for the closed loop system? Then we know we can count the number of pole D times G, the number of pole at the origin. Since GS contains no pole at the origin, therefore D times G has one pole at the origin. Therefore, the closed loop system is a type 1 system. Then for type 1 system, the steady state tracking error for step reference input is 0. To calculate the closed loop transfer function from R to E, we can use the formula forward path gain. It will be 1, then 1 minus the loop gain. Then it's 1 plus KIS times GS. Then it is S plus GS KI. Then we may choose Ki to improve the dynamic response, but too high Ki may make the closed loop system unstable. To find the final value of the control signal for unit step input, we can find the transfer function from RS to US. Again, we use the formula. Forward path gain is KIS, then 1 minus the loop gain. So 1 plus KIS times GS. That will be KIS plus GS KI. Then we can apply the final value theorem to find the steady state value of USS, the limit as approaches to 0, have S. Then we know the Laplace transform for unit step signal is 1 over S, then times the transfer function KS S plus GS KI. KS cancelled. So when S is 0, KI is cancelled. So the final value of the control signal is 1 over G0. That will be the inverse of the open loop DC gain. So it makes a lot of sense if you think in this way. The steady state tracking error E is 0. Then U will be 1 over G0. Then in the steady state, the DC gain of GS, it is G0. They multiply together. So the final value of the output is 1. The input is 1. So the output tracks the input. It makes a lot of sense to have the final value of the control signal is the inverse of the open loop DC gain of the plant. Now let's see the role of integral control for disturbance input. Again, let's assume the open loop gain of the plant is non-zero, means it contains no zero and no pole at the origin. Then the transfer function from the disturbance to the output is forward path gain. It will be GS. Then 1 minus the loop gain. So it is SGS S plus KIGS. Then the control input from W to U will be forward path gain is GS minus KS over S, then 1 minus the loop gain. It will be 1 plus KS SGS minus Ki GS S plus Ki GS. Now let's determine the system type for disturbance input. Then we need to know the transfer function from from WS to ES. So it will be, since when R is 0, so ES is minus, let's assume V is 0. So ES is minus YS over W, then it will be minus SGS S plus Ki GS. Since GS contains no 0 at origin, then we see the transfer function has a single 0 at the origin. Therefore, the closed loop system, it is a type 1 system for the disturbance input. So if the disturbance input, it is step signal, then the final value of the output is 0. Then we know for type 1 system, the step disturbance has no influence on the output. Then in this case, what will be the final value of the control signal? So we can calculate the DC gain of the transfer function. So it will be minus Ki G0 S is 0. So Ki G0 it will be minus 1. So it makes a lot of sense, because you see if the final value is minus 1, it means so US WS is minus 1. This means in steady state, the control signal has exactly the opposite sign of the disturbance input. So they just cancel each other when there are the two inputs to the summing junction. So there will be 0. So the output is 0, means that this disturbance has no influence to the output. Therefore, we have 0 steady state output error for both reference input and disturbance rejection. The final value of control signal cancels the disturbance exactly. We know that when we have the conclusion that when the reference input is a disturbance, when the reference input is step signal and the disturbance input is step signal, then the output can track the input at the steady state, and the disturbance has no influence to the output. We have the conclusion only assumes G0 has no pole and 0 at the origin. So we have no assumption about the parameters. Therefore, even though there are parameter changes, okay, we still have the same conclusion. So we can refer to this property as the robust robust property. So the integral control caused the closed loop system to become type 1 system. So if the reference input is a ramp signal and the disturbance input is a step signal, then the closed loop system can still completely reject the disturbance, but for the tracking, there will be a tracking error. Here it shows the performance of disturbance rejection of integral control for step disturbance input. Here we pick the value Ki 0.5. So we see a zero steady state error in the output. It means the integral control can completely reject the disturbance input. So the disturbance has no influence to the output at a steady state. The bottom figure shows the control signal at a steady state. The final value of the control signal is -1, which cancels the disturbance exactly.